Okay, almost done here. Sorry, this video is longer than others. It's just a lot of new stuff to cover, but hopefully it's not too challenging. But feel free to reach out with any questions. So we looked at infinite and finite sequences. So just some vocab here. So consider the infinite sequence: a sub 1, a sub 2, a sub 3, all the way to a sub I. So the sum of all the terms of the infinite sequence is called an infinite series. Alright, so series implies sum. Sequence is just like the order of those, like just all those numbers, like in order. Alright, and it's denoted by this here. You can write it out like that with a dot 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 to the last term, or use summation notation, and notice how there's an infinity symbol on top. Alright, so that's how we find an infinite sum. And you might be wondering, well, wouldn't the sum of an infinite amount of numbers be infinity? No, that's not the case. And I'll leave you, I won't say why, I'll leave you wanting more for the next couple videos, but there are types of sequences where if you add the sum forever, so an infinite sum, an infinite series, it does equal a number, like a specific number, not infinity. Alright, if it's a partial, if it's the first n terms of the series, so a finite, the first n terms of a sequence, so a finite series, we can also refer to it as the nth partial sum. Alright, so that means, like, the nth partial sum is all the terms up until n. So if we look down at this example, alright, the third partial sum just means the first three terms. So, if we were doing the third partial sum, I would start with 1 here. I would plug 1 in to this formula, so we get 3 over 10 to the first power, and then plug in 2, so 3 over 10 to the second power, and then plug in 3 over 10 to the third power, alright, and stop right there. So this would simplify to 0.3 plus 0.03 plus 0.003, so that's 0.333, alright, so now it says find the sum, so implying, what if we did that forever? Well, pause and think about it, and you can see that if we kept doing 3 to the 4th, 3 to the 5th, 3 to the 6th, 3 to the 7th power, we would just keep getting a repeating decimal. So the sum of this infinite series is just 1/3. So I prefaced it earlier, I said it wasn't going to give it away of how an infinite series could have a specific number as a sum, but there's one example, and we'll learn more later on. Alright, and then last but not least here, we have like a little word problem. So we have a model of the population of the United States right there, where A sub n is the population in millions, represented with the calendar year. So n sub equals 0 is 1960. Find the last 5 terms of this finite sequence, which represent the U.S. population for the years 1993 to 1997. So, I mean, for this, you're not finding a sum, so you don't need to use sigma notation. What I would do is I would just use a function. So do a sub n, and then do control : equals, and then type in that function as it looks. So 33,282 plus 801.3 times n plus 6.12 n squared. Alright, and I'll say done. So since it says the years 93 to 97, that would correspond to the numbers 33 to 37. So if we find those values, we can find the populations of the United States for those years, and realize that it's the population in millions. So that means in the year 1993, the U.S. population was 257 million people. All right, so how can we approximate the population of the United States now using this model? If you need time to think, pause the video. Well, the year's 2020, so that would be, 1993, that would be like A sub 60 would be the year 2020, because it's been 60 years since 1960, and we see 321 million. Let's see how accurate that was. Population of the USA in 2020. 331. So not bad, considering that model was created 60 years ago. It was pretty close to approximating the population today, only off by about 10 million people, which seems like a lot, but when it comes to predicting things, not that bad. Alright, I hope you found these helpful, and take care.